we'll look more in depth at the CADDIS approach now. We'll really cover it today and Wednesday. What we've done so far is we've talked a lot about the data that we've collected, even before collecting the data, looking at the watershed, identifying what potential pollutants and candidate stressors might be, and then collecting the data itself, benthic data, water quality data, habitat data, and then beginning to look at, as we covered last week, some of the different ways to analyze that benthic data, different ways to present it, different ways to analyze the water quality and habitat data as well. And so what we'll get to this week is now beginning to identify what are our prime suspects, okay? And using a weight of evidence approach to identify what those prime suspects are, or as we call them in the stressor analysis, the probable stressors. And the approach that I've used in several of the benthic stressor analysis for DEQ and what some of the regional TMDL coordinators have used just recently, Nesha in the Valley and Lucy in the Blue Ridge office, and Sarah, and we've been working with Sarah up in the Northern office as well to incorporate CADDIS into some of the ongoing TMDL benthic stressor analysis in those regions. So what is it? It's really just a framework. I think there's been sometimes in talking with folks, I get a little bit of a sense that there's a kind of a mystique around it, that maybe it's somewhat of a black box, that information gets put into this black box and then, you know, an answer, or as the title describes, a decision pops out of this box. Well, that's not really the case. There's no black box. There's really no automated decision system. What it is, it depends on the user, the analyst, whether that's me if I'm doing the stressor analysis, or if it's you if you're doing the stressor analysis. And all of these decisions depend on you. And so you're making those decisions, but you're really doing so just within a framework, a very organized, methodical framework that lets you identify all of the potential causes, analyze all of the lines of evidence for each of those potential causes, and then summarize and categorize the results from that. It is a weight of evidence approach, just like DEQ is used for a long time now. And I mean, that weight of evidence approach, like the analogy that I've been using in a crime scene investigation, weight of evidence approach is what we use in a court of law, right? We start with a hypothesis that you're innocent until proven guilty. And then we have a prosecuting attorney that presents all of the evidence that refutes that hypothesis. And we've got a defense attorney that presents all of the evidence that supports that hypothesis of not guilty. And then the jury has to, or the judge has to make a decision. Where does all of the weight of evidence, where does it point? And like I said, at DEQ, we've been using weight of evidence approach for a long time for stressor analysis. But I think up until recently, it's been a very kind of ad hoc weight of evidence where we look at a lot of data, we present a lot of data, but then we kind of say, well, this is the primary stressor, or this is the most probable stressor. Kind of trust me, I'm the expert. I've looked at all the data, and this is what we've decided. I think the benefit and the advantage of the CADDIS approach is that it's really systematic and comprehensive. It provides a step-by-step process to make sure that we evaluate all of the relevant evidence. And a lot of times, you know, when we do it kind of on an ad hoc basis, you know, maybe a stakeholder will say, well, you know, yeah, okay, you said it was sediment, but it looks like there's a little bit of evidence, you know, there were some high phosphorus levels in this stream. And we would kind of say, yeah, that's true. Yeah, there were a couple high phosphorus levels, but the weight of evidence says sediment. And I don't know if that's completely satisfying for a stakeholder. One of the advantages the CADDIS approach is you can point to, yes, here's where we considered that. It's very transparent for stakeholders. You can point to exactly where and how you evaluated every piece of evidence. I think collectively it kind of reduces some bias as well. It's not 100% bias free because we're still putting our own best professional judgment to bear on the questions of each piece of evidence. But I think by making it more systematic and comprehensive, I think it does reduce that bias because we're kind of putting down in writing what our decision is about that particular line of evidence. And in doing that, we kind of are able to check our biases, and they don't just go as unchecked biases. Another ability that the CADDIS approach has is we can formally treat uncertainty. We talked a little bit before about different sources of data. Maybe we have DEQ data, maybe we also have data from other stakeholders, maybe we have citizen monitoring data. Some of that may be of different degrees of quality and QA. We can accommodate that in the CADDIS approach because part of the scoring depends on what is your certainty with that particular piece of data. And I think all those things put together at the end provides a more scientifically defensible approach. So that's why I'm in favor of it. In terms of the different steps in the process, and we've talked about this one before, but the first step is identifying those candidate stressors. Ideally, this will be done even before you get to the actual CADDIS approach, and ideally done before the TMDL sampling plan, so that to make sure that you've collected the right information, collected the right data, so that you have enough to evaluate. And then the second step is to evaluate different lines of evidence. And each of those really represents a specific way to look and evaluate the data. And in the handout, and I'll go and I'll pull this up for you. In the handout, I've put together a list of those. There's 18 different lines of evidence within the CADDIS approach. 10 of them, which I've kept in white background. 10 of those are commonly used with the DEQ data that we typically have. There's another 8 of those 18 that I've put in gray. In most cases, we don't have data from our typical DEQ sampling and analysis. We typically don't have data to evaluate those 8 lines of evidence, but sometimes we may. So I've included them in there, but just in a different color. So let me share this with you. And this may be a helpful guide to you that you can pull up from the handouts. What I've done is listed in the far left column each of the lines of evidence, and they each have a little descriptor as to what that line of evidence is. The first one is spatial co-occurrence. Then for each, I've described what that concept means. And then in this column, available data and analysis, what are the typical types of data that we have in a TMDL project that can be used to evaluate that particular line of evidence? And then in the far right column is kind of an example of what a rationale might be for a given candidate stressor. This is kind of an example of what a rationale might be in a CADDIS analysis. So in this case, this first one, spatial co-occurrence, we'll look at all 10 of the ones in white here. We'll look at all 10 of them in detail in this particular lecture. But I just wanted you to get a sense of maybe what some of the grayed out ones are. So here's one of evidence of exposure or biological mechanism. What types of data might we use for that? Well, if we're looking at PCBs or maybe metals, any type of fish health or fish tissue body burdens could be a line of evidence. Again, we don't necessarily have that for every TMDL project. Here's another example, laboratory tests of site media. If we have toxicity testing data, there's a particular line of evidence where that type of data can fit in. But others are like manipulation of exposure. This is where we've either intentionally or unintentionally manipulated something in the watershed that would change the candidate stressor that we're looking at. And then we're evaluating, did VSCI scores change in response to that manipulation within the watershed? And a lot of times we don't have those types of controlled manipulations of the watershed. So that's a line of evidence that we likely aren't going to have. But there are some, like toxicity testing, we may have some of that data. We may have some fish health or fish body burden data, particularly if we're looking at PCBs or maybe some metals. But the ones in white are ones that we're likely going to have at least some data to evaluate those lines of evidence. All right, so let's start walking through what these 10 most common lines of evidence are. I mentioned before, the first one is spatial co-occurrence. And what we're doing here is we're really looking at, just like we talked about last week, a spatial analysis of both our benthic data as well as our water quality data. And so this is why last week I talked about some of the importance of having multiple sites within a watershed, as well as having a reference location within the watershed, because once we have that, now we can do a spatial comparison. And what we're really looking for is where we see high levels of the candidate stressor, do we also see impaired benthic communities? And if we do, then that's support for that particular candidate stressor being one of the probable stressors. Okay, and so next, after we have a question break, the next thing we're going to talk about is how we score these. But first, what I want you to do is just get an idea as to what is it that we're looking at in this particular line of evidence, and then we'll talk about how we score them. Okay, but for this one, we're basically looking at which sites did we see high levels of the stressor, and at those sites, do we also see low VSCI scores? And so down at the bottom, here's some examples of data from spatial analysis that might support this particular stressor as a stressor, and then some data that would refute it. So what we see is, if we have sites that are impaired and the levels, in this case, this example is sulfate, those levels of sulfate are much higher in the impaired sites than they are in reference sites. That's one line of evidence that sulfate could be a stressor. If, on the other hand, we see, well, between our impaired sites and our reference sites, we really don't see much difference, that would be a line of evidence that refutes, in this case, sulfate as being a stressor. Now, also notice that we could have seen in this refute, what if the reference and the impaired site both were up here in the median probability threshold level? That again would be evidence to refute sulfate as a stressor. In that case, what we're probably dealing with is some type of maybe underlying geology or something within that watershed that causes both high quality benthic sites as well as impaired benthic sites within that watershed to show high sulfate levels. And even though they both may be high, again, that's actually evidence of refuting sulfate as the stressor, because in one case, with those high levels of sulfate, we still see good, healthy benthic communities. So that's the first example. The second line of evidence is temporal co-occurrence. So again, when we looked at water quality data, one of the ways we said we wanted to analyze water quality data is through time. What do the levels of each candidate stressor look like over time? And do we see particular times where we see excursions of that stressor or that candidate stressor above or below certain thresholds? Now, that could be above or below thresholds from the benthic stressor tool, or that could be thresholds from the literature, or that could be water quality standards. Any of those thresholds could be used, but what we're doing is we're looking over time, and we're also comparing when did we collect benthic samples. and at and around the time that we collected those benthic samples and saw impaired conditions, what were the conditions of that particular candidate stressor at that time, or maybe shortly before that time? And so in this particular example on the bottom left, we've got, here's where we had 3 different benthic sampling events indicated by the arrows, and on or just before each of those, there were pH measurements that were below the water quality standard of 6. Also, in this case, that water quality standard also aligns with the stressor threshold probabilities. And so in each case where we see impaired benthic communities at that same time or around that timing, we also see excursions of that particular candidate stressor. On the right-hand side, we don't see that. We see, well, all throughout the time period, pHs are, within low probability ranges. They're not violating water quality standards. However, at those times when pH is not violating water quality standards and it's not, we're not seeing excursions out of the threshold ranges, we're still seeing impaired benthic communities. So that's one line of evidence that would, in this case, refute pH as being a stressor. All right, the third line of evidence is called causal pathways. Now, we haven't really talked much yet about causal pathways. And in Wednesday's training, we'll actually get much deeper into developing these causal pathways. I think they're actually very helpful in trying to identify what probable stressors are, and also in kind of presenting your case to stakeholders as to what the primary stressor might be. The idea of a causal pathway is really to connect, draw from dot to dot, right? Connect the dots from a source of that stressor to the individual responses to that stressor within the ecosystem, from one to the next until we get to what the primary cause of impairment is. And so if you look down the bottom left here, here's a very simple causal pathway for sediment. And so we see at the top, stream bank sediment, that's the source. There may be other sources of sediment. In this case, we're looking at just at stream bank sediment. Well, that stream bank sediment can be eroded. Okay, so that's kind of the next step in the connect the dots link to having a sediment impairment, right? That stream bank sediment has to get eroded. Now, there's some other contributing factors that increase that. In this case, we show high percent impervious area as one of those contributing factors. And how does that impact stream bank sediment? Well, it increases velocities, and those increased velocities then accelerate stream bank erosion. Once we get that stream bank erosion, that means that we now have an increased sediment load. That's our actual stressor. And then the impact that has on the benthic community is that it fills in interstitial spaces between rocks and gravel and cobbles and really reduces and eliminates habitat. And so if we can put together this causal pathway for a particular stressor and show each link in the chain of how it goes from a source to ultimately impacting the benthic community, then we can look and see, are there evidences of each step along the way? And so in this particular case, maybe we have, from watershed analysis, we have evidence of high percent imperviousness. Okay, maybe we have visual evidence of stream bank erosion, or maybe even some modeling evidence of high levels of stream bank erosion. Increased sediment load, maybe we have TSS concentrations in stream that are very high during storm events and higher than at reference locations. That's another link in this pathway. And then finally, sediment filling in interstitial spaces. Well, If we have habitat data that shows high embeddedness, we have evidence for that particular link in the chain. And so if we can show links and show evidence for each link in the chain, that's good support for that particular stressor from the causal pathway line of evidence. On the flip side, okay, let's say we have, in this case, the same causal pathway, but in this particular stream, we don't have any evidence of high impervious area, high percentage of imperviousness. We don't have visual evidence of stream bank erosion. Maybe our habitat scores for riparian vegetation are high, and our scores for embeddedness are very low. That kind of refutes this particular causal pathway as being a line of evidence for sediment. And so for each candidate stressor, we want to think about what are the links in the chain that would lead that particular stressor from some source in the watershed to ultimately impacting the benthic community. And then we want to look for evidences along those different lines, those different links within the chain. If we see evidence that supports each link, that would support. If we don't see, or maybe we've got a missing link in the chain, that would refute this particular line of evidence. Number 4, the fourth line of evidence is called stressor response relationships from the field. Okay, so this is a little bit similar to our spatial analysis and spatial co-occurrence, but in this case, what it's saying is it's really looking at the magnitude of response of the benthic community. And what we should see is as the magnitude of our candidate stressor increases, we should see the magnitude of impairment of the benthic community increase as well. Or said the other way, flipped upside down, VSCI scores should go down as this particular candidate stressor concentrations go up within the watershed. And so again, if you have multiple stations within the watershed, you can do correlations across those stations and do VSCI scores correlate with any particular stressor within that watershed. Okay. In this particular case on the bottom, here's some data for conductivity versus VSCI scores. And in this particular watershed, 6 stations within the watershed, as the average conductivity at those stations increased, VSCI scores decreased. Okay, so that's good evidence to support based on the stressor response relationship, good evidence to support, in this case, conductivity as a stressor in this particular watershed. If we don't see any correlation and we see, maybe we see a wide range of VSCI scores, but not very wide range of a given candidate stressor, that might be indication that, you know what, this particular stressor isn't controlling VSCI scores within this watershed. If it were, we would see that as the level of that stressor goes up, benthic scores go down. So again, that would be evidence to refute, in this case, conductivity as a probable stressor in this particular watershed. All right, number 5, line of evidence number 5, temporal sequence. All right, so what are we looking at in terms of temporal sequence? It's somewhat close to the second line of evidence that we looked at, which is temporal co-occurrence. There we were looking at the time when benthic scores were observed to be low, what were the conditions in the stream at that time or around that time? Temporal sequence, the concept here is that the cause must precede the biological effect. So here we're really looking at what has happened prior to benthic responses. And so one of the types of data we can use here is our seasonal analysis of benthic data. We said before that many times we see differences between fall and spring benthic scores. Maybe we see spring scores higher than fall scores, or maybe we see fall scores higher than spring scores. Well, again, that can be a potential line of evidence for or against certain candidate stressors. In this case, we show dissolved oxygen data, where in this particular stream, we see low dissolved oxygen throughout the summer and early fall. All right, beginning in, so here's July, so August, September, October, November, we've got very low dissolved oxygen conditions. And at the same time, if we look at our spring versus fall benthic data, we see much lower benthic scores in the fall. As a matter of fact, in the spring, we're almost non-impaired. This would be a line of evidence supporting, in this case, dissolved oxygen as a stressor within the watershed, because we see that as a temporal sequence, the cause, in this case, dissolved oxygen, precedes the biological effect. Late summer, fall, low dissolved oxygen leads to fall low scores. Some other, if we had a flipped condition, maybe spring scores were lower than fall scores, that would be evidence that that would refute dissolved oxygen as a stressor. Or let's say we see not much difference between spring and fall scores, and we don't see, we see our typical dip in dissolved oxygen during the summer, but we really don't see anything different in spring and fall scores. That would be a line of evidence that would refute dissolved oxygen as a stressor. Number 6, this line of evidence is called symptoms. And what that means is, do we have biological measurements, okay, that can be characteristic of one or a few specific causes? So here we're really looking specifically at the benthic data. And do the benthic data give us any indications as to what the stressor is? This is a great place for biological condition gradient analysis to be used. That's really what it's designed for. It's designed to look at the benthic community and see, based on tolerance levels for the organisms that we see there, do those tolerance levels indicate a particular stressor? Also, the benthic individual metrics, community composition, functional feeding groups, those are all potential types of data and analyses that are very useful in this particular symptoms line of evidence. So in the bottom here, I've showed some functional feeding group data. And on the left, again, the way to read these area charts, the left-hand side of the graph are reference conditions. The right-hand side of the graph is the impaired station that we're concerned about. And in this case, what we see is we see an increase in filterers and we see an increase in scrapers as we move from reference conditions to impaired conditions. And one of the indications, what that tells us, if we're seeing more filterers, more scrapers, that's a possible indication of nutrient enrichment. Because as nutrient levels increase, you'll get more algal growth on rocks and cobbles on the substrate. That'll increase the food that's available to scrapers. Also, as you have a more enriched environment, that's going to increase the amount of food that's just flowing down the stream. And so filterers will typically thrive in those particular conditions as well, and their percentages will increase in the community. So in this case, for the nutrient stressors, this would be support for the symptoms line of evidence supporting nutrients as a stressor. On the flip side, here, we don't see any increases in filters. We don't see any increases in scrapers. Scrapers are about the same. Filters decreased a little bit. But what we have is we have a large increase in collectors. Okay, this might refute nutrients as a stressor, but it might be support for sediment as a stressor. And so we're going to look and evaluate functional feeding group data, community composition data, and biological condition gradient data to see what evidence it provides in terms of likely stressors. Number 7, this is a line of evidence called stressor response relationships from other field studies. All right, so the concept here is that at the impaired site, the cause must be at levels that are sufficient to cause biological effects that we've seen at other field studies. So what type of data would we use for this? Well, this is actually a great place for the stressor thresholds and the benthic stressor tool data to be used, because what that really is it's looking at the stressor response relationship from other studies. In this case, from ProbMon data. We've got ProbMon data from all over the state, right? And we're saying what levels of particular stressors or pollutants, what levels of different pollutants were observed across the ProbMon data, and how was that associated with biological effects at those stations. So it's a great use of data for this particular line of evidence, stress response relationships from other field studies. In this case, the other field studies is really the analysis of ProbMon data. Okay, and so down at the bottom, these are some graphs that might come directly out of your benthic stressor tool. Okay, and we can evaluate, where were data in the high probability range for stress effects? How often was the data in the medium probability range, or the low or the no probability range? If we see a lot of data in the high probability range, that's good support for that particular stressor as a stressor according to this line of evidence. We probably also want to look at what the medians are, because the ProbMon data and the stressor threshold analysis document that was based on median values. And so we want to look over time, how do values of that particular pollutant fall out in the different ranges, but also where does the median and what are the bounds. On the right-hand side, here's a case where, well, looks like all the data we see is within the no to low probability threshold. That's evidence that, in this case, refutes this particular stressor, which in this case is dissolved sodium. This would refute dissolved sodium as a probable stressor in this watershed. So I said before, the benthic stressor analysis, the benthic stressor tool, in and of itself is not the stressor analysis, but it's a piece of it. Well, here's an example of where that piece fits in within the CADDIS approach. It's one line of evidence. We've also used it to evaluate some other lines of evidence as well, like the spatial co-occurrence and even temporal co-occurrence. So here's the 8th line of evidence. This one's called stressor response relationships from laboratory studies. Okay, and so similarly to the last one, what we should see is that the cause, or the pollutant, the candidate stressor that we're looking at, it must be at levels that are associated with biological impairment in lab studies. Well, what kind of lab studies do we have? Well, this is a good place for water quality standards to come into the analysis. How were most of our water quality standards developed? Well, they were mostly developed from laboratory studies looking at thresholds of different organisms, and then based on that accumulated data of different organisms and tolerance levels, the water quality standard was based usually on some statistical determination from all of that data. So I think that water quality standards can fit in nicely with this stress response relationships from laboratory studies. Okay, you could also use data from other literature values or literature threshold values. If you search the literature and you find, oh, here's a laboratory study that looked at pH, or maybe looked at some other parameter and developed some thresholds based on that parameter. That could be used as for this line of evidence as well. Okay, and so down at the bottom here again, we've got pH, and in this case, we've got the upper and lower water quality standard values, and we see pH values are frequently below the water quality standard. That's good support for pH as a stressor based on this line of evidence. On the flip side of that, on the right, if we don't see any violations of the water quality standard, that's evidence that refutes pH as a stressor in this watershed. All right, number 9, analogous stressors. What does this mean? Well, agents that are similar to the causal agent at the impaired site should lead to similar effects at other sites. So this kind of relies on what are some analogous stressors and what are some analogous stressor pairs that we might see. And here's some that I provided for you. Conductivity and dissolved ions and total dissolved solids. If we see evidence for one of those, we should probably see evidence of the others as well as stressors. pH, acidity, alkalinity, those are analogous stressors as well. And where we see one, we should see the other. Organic matter, TOC, total organic carbon, volatile solids, those again are analogous pollutants. And if we see one and suspect one as a stressor, we should probably see high levels of the others as well. Dissolved metals and sediment metals. If we think that metals are an issue in this particular stream, we're probably likely to see them in both the dissolved form and sequestered in sediments. Phosphorus and chlorophyll A. Again, if we see phosphorus as a potential stressor, we're probably going to see chlorophyll A issues if we have lakes or reservoirs within the watershed. And so what we're looking for is, do we see the same patterns in those analogous stressors as we do in the candidate stressor? So evidence to support that would be on the left at the bottom. We see, in this case, arsenic exceeds water quality standards in the water column, and we also see arsenic in the sediments. To refute that, let's say we have a couple readings of dissolved arsenic that exceeded the water quality standards, but we don't see any arsenic in sediments. Or if we do see it, it's below probable effect concentrations within the sediments. That would be refuting arsenic as a stressor in this case, because we don't see the same pattern in the analogous stressors. And then lastly, number 10, this is called consistency of evidence. What this means is that the confidence in our argument for or against a cause is increased when many types of evidence consistently support or refute it. And so what we're doing here is, after we've analyzed the other lines of evidence, we're going back and seeing, okay, how consistent are we in either supporting or refuting each candidate stressor? If we see, wow, as we've looked down each line of evidence, we've seen pretty strong support for this candidate stressor, then that would also provide support for this line of evidence, consistency of evidence. If, on the flip side, we see a very mixed bag, we see in some cases, some lines of evidence supporting it, other lines of evidence refuting it, we would probably give a low score for consistency of evidence. Okay, so this is kind of acts like a weighting factor. It kind of is a multiplier, because if we're seeing consistent evidence to support it, this will provide another line of evidence in that same direction. So those are the 10 lines of evidence that we're likely to see with DEQ data. If you want examples of the others, you can go to that particular handout and look at the ones that we're not likely to see in DEQ data. But I think this is a good opportunity now to pause for any questions that you might have.
Robert, we do have one question. Does a summary of the FFGs exist anywhere so non-biologists can understand what they're seeing in that line of evidence? Obviously, we should work with our regional biologist, but it would help just to gain a basic understanding.
Yeah, I haven't put anything together formally with regards to that. Like the question said, I would encourage you to get together with your regional biologist and discuss that. I've shared a couple in the lectures. I've shared a couple common scenarios, and that is for nutrients to increase scrapers and filterers, and for sediment to increase collectors. But what happens when you have both? What happens when you have nutrients and sediment? You can see kind of a mixed bag in the biological community. So that's a good suggestion. I haven't put anything together formally based on that yet. Maybe that's something for the to-do list.
Some parameters can be evaluated using many lines of evidence, but others cannot. How do you get around overweighting the parameters that can be evaluated by many lines of evidence?
Yeah, that's true. So for some pollutants, we'll have more data and we'll have more lines of evidence to evaluate. And that's just what it is, right? And so for those, we should be able to be more certain about our determinations because we have more lines of evidence either supporting or refuting it. For particular stressors that we don't have as much data for, I think that gets at how certain are we about our determinations. You know, if we only have a few lines of evidence supporting it, we'll typically end up with scores, even if it falls out as a stressor, we'll end up with scores that are lower. And so that's kind of an indication to you as well as to the stakeholders that, yes, we've identified this one as a stressor, but our confidence in that is a little bit lower than what we see for maybe some of these other stressors.
Okay, great. Can you talk a little bit about the expected recovery period for benthic communities after acute events like large storms or large temporary drops in DO?
Boy, that might be a good question for your regional biologists. From my experience, you know, benthic communities can recover probably within weeks to months is probably the time frame for recovery from a single one-time episode, maybe a high flow scouring event, maybe some type of toxic event. It's probably not on just the order of a week or a couple weeks, but probably on the order of weeks to months in terms of recovery. Because it's going to take time for those upstream organisms to drift and recolonize that particular location.
I was just going to add that I can add a little bit to that. My past experience with acute events causing benthic communities to crash, at least in terms of certain species, if not the whole complement of the community, can take a pretty long time. Usually, like Robert suggested, that it happens within weeks to months in some cases, but it depends on when the event happened in the season sometimes, because bugs are sometimes seasonal in their reproduction, and many species that are long-lived that are benthics that live a year or more and as a larval stage will take another year at least to recolonize at all. So it could be, you know, a year and a half before you'll see those bug species reoccur if they come back at all in the community.
Yeah, and an important factor there too is, do you have upstream colonization sources? So do you have somewhere that was not impacted upstream that can provide a source of colonizers? And if you don't, then it's going to be a lot longer before you see recovery.
Yeah, absolutely. That's a good point, and in that light, it makes us realize how important impoundments and things that block water flow or cause it to change to a situation that doesn't produce enough oxygen, say in a lake where certain species won't survive and will not be subject to drift downstream. So it's a good thing to think about in terms of how it interacts with other, alterations in the watershed.
All right, so here's our next step in the CADDIS approach. We've looked at the different lines of evidence. We've decided what type of analysis, what type of data will fit into each of those lines of evidence. And now it comes to scoring it. How are we going to score it? Well, there's two different general types of scoring. We have symbolic scoring or numeric scoring. Okay, symbolic scoring is basically where for each line of evidence and each candidate stressor, we're going to put some pluses if it supports it, and we're going to put some negatives if it refutes it. For numeric scoring, we're actually going to give it a numerical score. In this case, for things that support it, we're going to give it a score from 0 or from 1 to 3 in the positive. If it refutes it, we're going to give it negative numbers from -1 to -3. Okay, and that's based on the strength of how strongly it supports it or how strongly the data refutes it. All right, so what's the difference in comparing these two approaches? EPA actually recommends the symbolic scoring approach. And the reason they do that is because they don't want to imply a particular score has specific meaning, right? A score of 10, what does that compare to in this watershed to another watershed? Well, see, the scores, if you use numeric scoring, are really only relative. They're only relative to the lines of evidence being investigated. They're only relative to that particular project. Okay, so it's difficult to say, well, a score of 10 here is equal to a score of 10 over here, because you have different data sets. You may be looking at different lines of evidence. And so for that reason, EPA actually recommends the symbolic scoring approach. Okay. I've actually used, and I actually recommend the numeric scoring approach, as long as you keep in mind that those scores are really only relative. Okay, they're only relative to the lines of evidence investigated and the data that's available in each particular case. The reason I typically like the numeric scoring approach is I think it's more easily understandable by stakeholders. If you have a score of +3 and +2 and +1, you add those together and you get a score of +6. That's pretty intuitive to understand. In symbolic scoring, if you have a 3 pluses and then another 2 pluses and another 3 pluses, what does that equal? Well, it equals 2 pluses. How does that work? I don't know exactly. So I think it's a little easier for stakeholders to understand. And I think it also better represents the cumulative weight of evidence. All right, so what are things that we want to consider when we score evidence? The first thing we want to consider is the magnitude. Okay, so how far does the observation deviate from background or reference conditions? And so here's some examples. Let's say that we're looking at dissolved oxygen and we see some dips in dissolved oxygen. Well, was that dip down to 6.2 or was it down to 3.7? If it was down to 3.7 versus 6.2, that would be a higher score because the magnitude of that evidence is increased. In this case, decreasing is an increase in, we would consider an increase in the magnitude of the evidence. Second example, so what if we're looking at feeding guild analysis? Okay, and scrapers increased by 50% versus maybe they increased by 10%. In both cases, they increased, right? So that might be some evidence of support for nutrients as a stressor. But if they increased by 50% versus 10%, I'm probably going to give a higher score, right? Both might be positive scores, but maybe it's a difference in a +3 versus a +1. And then lastly, for example, for phosphorus, maybe a phosphorus concentrations that averaged 3.2 milligrams per liter. Okay, very high phosphorus levels versus, well, maybe the levels were 1.3. Again, the magnitude of of the evidence should be evaluated in terms of scoring. The higher the magnitude, the greater the score, the greater the support or level of refuting. So aside from the magnitude of the evidence, we also want to look at the repeatability of the evidence. How often is that particular piece of evidence displayed, either in time or space? Okay, so again, some examples would be, what if we have 70% of your observations are within the medium probability range for stressor effects versus we have just one observation within that range? Again, this is how the amount of data that we have can play into the CADDIS approach and can play into our decision making. The more data we have and the more of those observations that we see above a certain threshold, that adds to our sense of confidence, right? And how does it do that? Well, it does that through higher scoring for repeatability of evidence. So that was kind of through time. It could be through space as well. Example, the second example says that 3 sites in the watershed exceeded water quality criteria for pH versus only showing that in 1 site. So again, we've got more evidence from more sites supporting, in this case, pH as the stressor. And so that would provide, in this case, we're probably looking at the spatial co-occurrence as our line of evidence. Well, if we've got 4 sites where we saw high pH level or low pH levels and low benthic scores, that would probably give a higher score than if we only had 1 site, and at that 1 site we saw low pH and low benthic scores. So again, the repeatability of evidence can play into the analysis as well. And then the certainty of evidence. How certain are we that the data from this line of evidence points to the stressor? This is where we can consider the quality of the data. We talked before about citizen data versus DEQ data. Well, it can come into how we score each particular line of evidence. If we're relying on this line of evidence just from citizen data, maybe we give it a lower score, even if it does support or refute. And then this also considers the amount of data that we have. It also considers, are there other possible explanations? So for some lines of evidence, we may see that, for example, a low VSCI scores in the spring, that could potentially point to sediment, or it also could potentially point to nutrients. Sometimes some things that we see in benthic community composition analysis, if we see, wow, we're just missing, we're missing all of our EPT taxa, our Ephemeroptera, Plecoptera, Trichoptera, they're all gone. Well, that could be indicative of a number of different candidate stressors. And so because of different possible explanations, that would lower our certainty of that particular line of evidence. And that would also lower our score for that line of evidence. So are there other competing explanations for what we see? What's the quality of the data that we see? And what's the amount of data that we see for that line of evidence? All things that can factor into our score. So here's an example for you on how I might score, in this case, this line of evidence would be the stress response relationships from other field studies. Okay, so in this case, we're looking at the benthic stressor tool data. We're looking at the stressor thresholds, and how might we score data based on that. Okay, for this particular data set, we've got a median within the high probability range, and almost all the data is within that high probability range. That's definitely a +3. Okay, very strong evidence that this particular stressor, in this case connectivity, is above this stressor threshold. Now, it might get a +3 for this line of evidence, which is evaluating against the stressor threshold probabilities. But for other lines of evidence, maybe it has evidence that refutes it, or evidence that scores much lower. But for this particular line of evidence, I would give it a +3 score here. All right, moving down. For this particular second from the right site, here we have a median within the medium probability range. We've got some data that extends into the high range. We've got other data that extends into the low range. Okay, again, based on that median there in the medium range, I would probably score that as a +2. I think there is evidence supporting that it is a stressor. Here's a case where maybe our data is spread more broadly. We still have some data that's in the high probability range, but we also have data in the no probability range, and our median falls out in the low. But we've got a considerable amount, probably a quarter of data at least, that falls in the medium range and some values in the high range. Again, very weak score, but there is some evidence that maybe this is a stressor. Now, if we get down into this range, where maybe our median is maybe not much different than it was there, but we don't have any excursions into the high probability threshold range. Our highest excursions are in the medium range. I would probably give that a score of -1. -2 in this case, all of our data lies within the no to low probability range. We don't have any excursions into the medium or high range, and our median could be either in that no or low range. Getting a little bit stronger evidence that this particular stressor, conductivity, is not a stressor in this watershed, and then a score of -3, like the strongest score of refuting conductivity as a stressor. I would probably give when I see, looks like, okay, most of the data, almost all the data is in this no probability range. Maybe we even see some excursions in the low range, but definitely no excursions into medium range. So those are some examples of how I would score those types of data for this line of evidence. All right, so that concludes scoring. We've got another opportunity now for questions if you have them.
How should citizen data be scored? Should it be scored differently than DEQ data?
So usually we're going to probably have some citizen data and some DEQ data, and they may be for the same parameter. So one of the things we want to look at is, does the citizen data come to the same conclusion that DEQ data comes to? And if so, then that's actually, the citizen data is actually supporting and adding more support to the DEQ data that we have. If we see, oh, well, citizen data found maybe some violations of a water quality parameter in a place where DEQ did not have any data, maybe it's a site that DEQ doesn't monitor, that's one place where the citizen data could be used to support a particular pollutant as a stressor. But again, we want to look at what's the quality of that data. And if the quality, maybe it's level 2 data, not level 3 data, even though if it was like very strong evidence that that water quality parameter violated a water quality standard, we might want to give it a low score though, maybe a +1 rather than a +3, right? If at that same location we had DEQ data that showed, I don't know, 5 violations of the water quality standard, maybe we would score it as a +3. But if we only had citizen data that showed violations there, maybe it's a lower score, maybe it's a +1 rather than a +3. So again, it depends on how much data, what's the quality of that data, how does it fit in, and how does it compare with what DEQ might have collected at that station or nearby. But it does give it, the nice thing about the CADDIS approach, it does give us that ability to evaluate the score based on the quality of data. But that's a decision that we have to make as the analyst.
We have more questions? Oh, here. How do you address very limited data sets when using the CADDIS approach?
Well, it goes back to day one, right? Where we said more data, more places over more time. The more data we have, obviously, the better. When it comes to the CADDIS approach, we use the data that we have. And there's not a lot of ways around that. We still score it the same way we would score it otherwise. But maybe we only have a few lines of evidence that support or refute candidate stressors. That just limits our confidence in our results, which I think it always has. I think that this just provides a more systematic approach to showing maybe the lack of confidence that we have in our decisions. But there's really nothing special you have to do or don't do in the CADDIS approach to accommodate a small amount of data. It just means you probably won't have some lines of evidence to evaluate. For a given line of evidence, if you have a small data set, that will play into the score. And so the scores might not be as high or as low based on smaller data sets.